For years as a ham, I've never really understood how noise couples onto a coax line and gets into your receiver. So over the last couple of days, I've put a bit of effort in and tried to understand it for myself. And I've created a presentation that may help others to understand. It's not very polished, but if you gain any information at all, then it's a bonus. So first of all, I'd just like to go over a couple of points regarding coax cable. And there's three principles really that I want to talk about. The first one is that there can be actually three currents on a coax cable. Current flowing up the inner core. This is always balanced by an equal but opposite current flowing on the inside surface of the shield. And there can also be a separate current, which is labelled I3, which is independent completely of I1 and I2. And this is the common mode noise current that's often picked up on the outside surface of the coax. So some of these principles are a little complex. It does seem counterintuitive that you can have I2 and I3 effectively on the same bit of metal, but due to skin effect they travel very close to the surface on the two opposite surfaces of the coax. So having accepted that, let's just go on to describe a little bit more detail about I3. I3 is a current that can be impressed upon the external surface of the coax by a nearby noise source. And the impedance that it sees depends upon the actual length of the coax cable that is presented. For example, if you apply a noise current very close to the receiver port, which is assumed to be earth, then the impedance will be very low, i.e. near zero. The further you come away from the receiver, the more inductive it would look, until you get about a quarter of a wavelength away, and it would look high impedance, very inductive. You carry on going further backwards away from the receiver, it would then look very, very low again and go through a 0 point at half a wavelength. 3/4 of a wavelength, it becomes very capacitive, high impedance capacitive, and I think you get the idea, and I'm sure you've seen this sort of curve before, but this will crop up a little bit later in the presentation, so just bear this in mind. So I really want to discuss 4 mechanisms of how noise ends up within your receiver and causes problems when the coax runs close to some noise source within your house or shack or whatever. So a typical situation is something like this. We have a receiver, coax feed, and assume it's connected to a dipole. There's no chokes or balance or anything on this, and I've modelled the noise source as a voltage source with some capacitive coupling onto the external surface of the coax at some arbitrary point along the length of the coax, and there's a distance of L1 to the dipole and distance of L2 back to the receiver. If we formulate an equivalent circuit for this, the noise source creates a current through the capacitive coupling or whatever mechanism of coupling, some impedance. So we have a current coming out from the noise source, and you can see immediately after it goes through the coupling impedance there are 2 paths, either up L1 or down L2. Now ZL2 is the impedance that the that particular length L2 of wire will present back down to ground. So there will be a current flowing back down the coax towards the receiver on the outer surface of the coax, and it will flow into an impedance of ZL2, which is there. And the other arm of the other current will flow upwards towards the antenna, which is there, and that will have a different impedance, arbitrary, we don't know what it is really, but that's dictated by that impedance there. Once it flows through the length of coax to reach the feed point of the dipole, we're at this point here. Now we have the arm B of the dipole, which presents some form of impedance back down to ground. So we'll have a current flowing from that point down to ground, which I can label as that current there in ZB. And also we'll have a current which will flow through the 50 ohm input resistance of the receiver, and also through back through the arm A of the dipole back down to ground. So this would be this current here. So you can see how it's a little bit complicated, but you can see how that noise voltage has somehow caused a noise current to flow through the receiver. And this is the, or I'm led to believe actually from what I've read, this is perhaps the most significant reason why your receiver sees noise. So reading the text, the most significant cause of noise is the noise current in the outer shield flowing into the antenna at arm B and also through the receiver's input impedance and arm A to create a noise voltage across the 50 ohm RX input. So that's quite a, I suppose, a relatively obvious mechanism of the noise voltage and the currents causing a direct noise voltage in your receiver. So the second mechanism, if you can see point 2, another cause is due to the currents now flowing on the outer surface of the coax. They will themselves radiate and be picked up by the main antenna. So we've got within L1 and L2 portions of the coax, we've got these currents flowing, and they're not contained by any coax cable or any feeder. They're relatively free to radiate, and they do radiate. And of course, the proper dipole antenna is likely to pick these up, and that's another mechanism where noise is coupled into your receiver. It gets re-radiated by the outer surface of the coax and picked up by the dipole antenna. The third mechanism is due to the current flowing towards the receiver. So let's just read, oh dear me, let's just read number 3. So consider the current flowing towards the receiver. If there is any small resistance or impedance present in that earth connection, the noise current will cause a noise voltage to be picked up by the receiver. I've drawn a small diagram here to try and indicate what happens. In the coax, we've got the signal, which is I2 in the initial diagram of the coax. The I2 is the wanted signal, and the I3 is the noise signal. So the wanted signal on the inner surface now combines with the noise on the outer surface of the coax. They get mixed together in some common impedance that I've drawn as a small inductor which links the coax to the receiver 0 volts. Now, in theory, you wouldn't want any inductance at all. The designers wouldn't naturally put any inductance, but of course it's difficult to get zero inductance and zero resistance. And if it's a sloppy pigtail end of a coax, then this is what would happen. So the noise effectively gets converted into a real signal, which the receiver cannot differentiate between the real signal, and unfortunately you see it on the output of your receiver. So that's the third mechanism. The fourth mechanism is to do with the imperfect shielding of a coax. And if we read comment 4, since a coaxial cable doesn't have perfect shielding, the noise current on the outer surface will couple into the inner and impress noise onto the wanted signal. I guess it's easier to consider that if you're actually transmitting from a coax, you can somewhat imagine that if you get a small pickup loop by the coax, you will actually pick up quite a bit of signal. And I think we all realise that coax doesn't completely contain the transmitted signal. It does leak out by the imperfections of the shield. And this works in opposite mechanism when you receive. Some of the currents on the outside of the coax will be coupled to the inner of the coax, which of course is the real wanted differential signal, and of course that will get picked up by the receiver and amplified accordingly. So these are the four main mechanisms of why and how noise is coupled into your receiver. I don't want to finish there. I've got a couple of points that I want to mention, mainly about using chokes, because chokes is the usual method of preventing or stopping or limiting or reducing the amount of noise pickup. But I think there are some important points that are worth mentioning with chokes. Of course, it's obvious to think that if you use a choke to limit the current, add an impedance which would reduce the current, then you reduce the noise. But that may not be true, and this is what I want to look at in a little bit more detail. So I say add impedance to theoretically reduce these troublesome currents, and the general practice is to add a choke at just before the antenna at the feed point, and add a choke just before the receiver at the receiver port. I think it's considered that if you only have one choke, stick it near the antenna, and if you've got two, well, put one at either end. However, just a few notes, as I've mentioned, which you need to be careful of. Adding one at the receiver port, I believe, may well be counterproductive. Increasing the impedance here, which will occur if you add a choke, may well cause more noise current to flow towards the antenna and increase the noise. And I just want to explain that a little bit. If we look at ZL2 in the equivalent circuit, if we effectively make ZL2 a short circuit, then all the noise current would be decoupled back down to earth, so no noise voltage would appear across ZL2, and therefore no extra noise voltages or currents would be impressed into ZL1, ZB, the 50 ohm receiver, or ZA. So it would seem a good idea here to actually have, rather than a choke, actually have a zero ohm, a short circuit down to ground. And I believe that's true as long as you don't suffer from this problem here where you have some form of inductance or resistance or some poor grounding system at the input to your receiver. I think with today's modern receivers, I would imagine this is a thing of the past. Homebrew equipment may well have this issue, but I would imagine most receivers nowadays are very well designed and manufactured and mechanically sound, such that the inductance is limited. So I don't know. I'm guessing it's just a point to bear in mind that there's perhaps a counter argument as to why a choke may not be a good idea at the input to the receiver. And the other issue I have is that reading this second paragraph, chokes can be constructed in quite a few ways. They can be simple turns of coax or by using ferrite material. Although both will in their own right add impedance, there is a subtle difference. Ferrite usually works out to be resistive, whereas a coil of coax will be inductive. Inductive choking can be a problem because there's a chance it can be cancelled somewhat by a potentially capacitive length of coax. The result is worse than having no inductive choke at all. So what do I mean by that? Well, you can see a little picture below where we have an antenna and we've created a choke by wrapping a few turns of the coax together, which is a common method. But that produces an inductive choke, which on its own will add impedance or reactance, add ohms in effect. But of course, coming back to this graph, we could be in a situation where a particular length of wire actually between the noise feed point and the choke is actually a capacitive impedance. This is where the problem occurs, because the capacitive impedance will cancel the inductive impedance or reactance, and you'll end up with very little overall reactance. So you're not doing a very good job at all of trying to prevent any noise currents flowing up into the antenna. So just that's another point just to be aware of, that if you try adding coils of wire into your antenna system and you in fact end up getting more noise, then hopefully it might be something along these lines and you can take further action. So this is what I've learned over the last couple of days of delving into this subject. Please feel free to critique and correct me. This is just my understanding. I'm not saying it's right, but I hope that I've been able to give you a little bit more understanding of how I think noise becomes a problem due to, local noise sources being close to receiver coaxes. Thank you very much.